the first problem we were asked about at what time. So we have this circuit, and before time t equals 0, the inductor is completely uncharged. The circuit is completely uncharged. The switch is open. At time t equals 0, we close the switch. So close S. And we were asked about at what time t0 after t is equal to 0 does IL, which is the current through the inductor, reach 63% of max value. Okay. So if you guys remember, you know the graph of the current through the inductor looks something like this. At t is equal to tau, the current through the inductor is 63% of Imax, where this here is Imax. 63% of 62%. Okay, so all we have to do is find tau. Say t0 is equal to tau. To find tau, if you just look, we know that tau for LR circuit is tau is equal to over R. So all we have to do to find tau is look at the circuit from here. So we have a looking from here, and we know L is the only L in the circuit. So that's the L that we're going to use here, but we need to find R. R is going to be the equivalent resistance if you're looking from here. So if we have this circuit here, and you're looking at it from here, we're going to ask ourselves what's the equivalent resistance. So in this case, you still have the value of R3 here. We can move R3 here, it doesn't matter if it's in series with this segment, R2 here, and R1 here. So, the equivalent resistance of this circuit is simply R2 in parallel with R1, all that in series with R3. So let's come down here and solve that. R2 in parallel with R1 gives us R2 minus R1 over R2 plus R1. Series with R3. This is R equivalent. And so tau is equal to L over R equivalent, which is equal to L over R2 plus R1 over R2 plus R1 plus R3. And we're done. This is the value for time t0. Simple. For the next problem, we have the following circuit. And actually, we won't use these values because it doesn't really matter. We're just going to use the symbols. So step we'll be using this diagram here. We're going to ask questions like, assuming that T0 S, which is this guy switch, closed. This is IL. Don't do this. I can call it I sub 0, but really, I sub 0, find I sub 0 at 0, 0, I sub 0 at infinity. We can also get a voltage, let's call this VL. It's a function of time, of course, there's also a function of time. So VL, 0, and VL. Okay, so when we close the switch at time 0, close this. Right when we close the switch, the inductor is going to try to impede all your current. That means the inductor is going to act like an open circuit. So we can assume that this entire current is not here. So the path for the current is like that. So the current through the circuit, which is I sub 0. It's going to be V over R1 plus R2 plus R3 plus R4 because all of them are in series. This is I sub 0. This is I sub 0. And 2 0. Okay. Now, find I sub 0 at t equals infinity, and t equals infinity, the inductor is going to act like a wire. It's uncharged, it has no bits at all. All the current is going to be flowing through it. This is the current through your inductor time, and through the circuits, right? So we have no current flowing here because the resistance across the inductor is absolutely 0 because it's basically a wire. So a wire parallel with anything is going to be nothing. Now, at infinity, that means that no current flowing this branch. However, we can still find, let's assume that we're asked about IL, infinity, which is the current through the inductor. In this case, the current through the inductor is the inductor is a wire. The only thing that's impeding the current is going to be R1 and R4. So V over R1 plus R4. So I spell infinity. Another thing we can ask is, there's a voltage across the inductor at t equals 0. Voltage across the inductor at t equals 0 is the same as the voltage across. At any time, the voltage across this inductor here is going to be the same as the voltage across this branch from here to here. So this way. Because remember, KVL tells us that no matter what path we take, the voltage has to be the same. So voltage across the inductor is the same as voltage across the resistor, which is a current I sub 0 flowing through each resistor times the resistance. So VL time t equals 0, 0, I sub 0 times 0. I sub 0 at t equals 0, sorry. Multiplied by the resistor, resistances of R2 and R3. T is equal to infinity. Voltage across the inductor is still the same as the voltage across this branch, but we know that at time t equals infinity, there's no current flowing through this branch. Therefore, the voltage across V R2 plus R3 to R2 is equal to 0, therefore the out infinity is equal also equal to 0. So we're going to have no voltage at t is equal to infinity. The second, because the second we open the switch, again, we know that the current that's going through the inductor has to be the same. It means the inductor's voltage is going to increase from 0, because we just found that, we just found that the voltage across the inductor at t is equal to infinity 0. It means it's going to increase from 0 to whatever it needs to be to keep the current across it the same. So it may jump 200 volts